morning friends. We shall continue with the topic on parts of network functions. Yesterday we discussed about functions R omega being given, how to get ZS. Okay. So, we resolved this by substituting omega square equal to minus S squared. We took the roots in the left half plane and finally found out the coefficient of the numerator A0, A1 and so on. Now, today we shall be discussing about the magnitude function. If the magnitude function is given, how to calculate phase. Magnitude function is given to calculate, to determine phase. Now, the magnitude Z squared can be written as ZS into Z minus S at S equal to j omega. Is that all right? And what is ZS? If I write in terms of even and odd parts, M1 plus N1 by M2 plus N2. This is ZS. And what is Z minus S? M1 minus N1, it is only the odd part which will be having a negative sign now, divided by M2 minus N2. Is that all right? At S equal to j omega. So, what you are getting is M1 squared minus N1 squared by M2 squared minus N2 squared at S equal to j omega. Is that all right? So, if you are given Z magnitude squared, it is basically M1 squared minus N1 squared by M2 squared minus N2 squared at S equal to j omega. So, if I make a reverse substitution, I will get M1 square S minus N1 square S by M2 square S minus N2 square S from here. Okay. So, there if I factorize and drop out the roots in the right half plane, I will get M1 plus N1 and correspondingly M2 plus N2. It is very simple. So, let us take one example. Z j omega squared is equal to 1 plus omega squared by 1 plus omega squared plus omega to the power 4. So, that gives me, if I make reverse substitution, it will be 1 minus S squared by 1 minus S squared plus S to the power 4. Okay. So, what are the roots of this? 1 plus S into 1 minus S. Okay. What are the roots of this? S squared, see 1 plus S to the power 4 plus twice S squared minus 3S squared. So, it will be 1 plus root 3S into S square minus root 3S plus 1. Alright. Obviously, the quadratic with the negative sign, this is M2 minus N2, this is M2 plus N2, this is M1 plus N1, this is M1 minus N1. So, that gives me ZS equal to the left half plane roots, the factor corresponding to that is 1 plus S divided by this one, S squared plus root 3S plus 1. Is that all right? S 1 plus S by S squared plus root 3S plus 1. Realization of this, you can realize this by Bott-Duffin or Bruns synthesis. Okay. We are not going to the realization part at this stage. ZS is this much. Let us take another example. Z omega squared is equal to omega squared plus 16 by omega 4 plus 10 omega squared plus 9. So, I can write Zs into Z minus S as 16 minus S squared divided by S to the power 4 minus 10 S squared plus 9, which gives me 4 plus S into 4 minus S. This gives me S squared minus 9 into S squared minus 1, which gives me finally 4 plus S into 4 minus S by S plus 3 into S plus 1 into S minus 3 into S minus 1. So what will be Zs? 4 plus S by S plus 3 into S plus 1. Okay. Is this all right? Like this, you can see for any function, mind you, Z magnitude square will be a function of omega squared only. There is nothing like omega, omega to the power 3 and so on. This will be an even function of omega, this will also be an even function of omega. Next, we go to phase to magnitude. Phase to magnitude. Okay. Now, if I see the angle ZS, if I write as even ZS plus odd ZS, then Zj omega, this will correspond to a real part this is nothing but even Zs at S equal to j omega, and this gives me odd Zs, okay, at S equal to j omega. J will come out of this. Is that okay? So what is tan theta? You are given, say, the angle tan theta is odd Zs at S equal to j omega, but odd Zs will generate a j term, okay, mind you, divided by even Zs. All right. So this is nothing but, so if I write j tan theta, you will get n1 m2 minus m1 n2 divided by m1 m2 minus n1 n2, okay, at S equal to j omega. All right. This is nothing but, okay, suppose this is equal to this one, even Zs plus odd Zs is, say, after division and making a reverse substitution, suppose we get m by n, okay, m by n. So m plus ns, if the ratio is ms by ns, if it is ms by ns, then what is ms plus ns? This plus this, okay, which will be n1 m2 minus m1 n2 plus m1 m2 minus n1 n2, which means m1 plus n1 into m2 minus n2. Okay. So, the one with m1 plus n1 terms, that is roots in the left half plane, will be numerator, and roots in the right half plane will, if you shift those roots in the left half plane, that is m2 minus n2 you get. So, just change the sign of n2, that will give you the denominator. Alright. So, let us take an example, it will be clear. Suppose tan theta is given as minus omega to the power 5. Okay. So, we substitute omega is equal to s by j. So, j tan theta, we are computing j tan theta, that is minus j omega to the power 5, and that gives me minus s to the power 5. All right. So, this we are calling as m by n. So, s to the power 5 by 1, is it not? This will be s to the power 5 by 1 with a negative sign. So, what will be m plus n? 1 minus s to the power 5. Is that all right? So, 1 minus s to the power 5, what are the factors? 1 minus s. Now, let me work it out here. S to the power 5, no, you do it this way. 1 minus s to the power 5 equal to 0, you want to find out the roots. So, s to the power 5 is equal to 1. So, on the unit circle, so that is equal to e to the power j 2 pi n. So, what will be s? E to the power j 2 pi n by 5. Put n equal to 0, 1, 2. So, if I put n equal to 0, this is one root, then 2 pi by 5, 72 degrees, this is 72 degrees, 2 pi by 5, then 2 into 2 pi by 5, 144 degrees, okay. Then 3 into 72, so 216 degrees. So, the values are 1 e to the power j 72 degrees, e to the power j 144 degrees, e to the power j 216 degrees, e to the power j 288 degrees. These are the 5 roots. Is that all right? Obviously, 1 into e to the power. So, 1 to the power 1 by 5. So, that will be 1. They will all be on the unit circle. So, what are the factors corresponding to m1 plus n1? It will be this. This is giving me m2 minus n2. So, m2 plus n2 will be just images of this. So, m1 plus n1 will be s minus this e to the power j 144 degrees into s minus e to the power j, this one 216 degrees. All right. So, that gives me cos 144 degrees. Okay. That means this one, how much is this angle? 180 minus 144, 36 degrees. So, cos 36 degrees. So, s plus cos 36 degrees, and this will also give me cos 36 degrees. So, 2 into cos 36 degrees, so s square plus 2 into cos 36 degrees into s plus the imaginary parts alpha square plus beta square is 1, it will be 1. Is that all right? Any quadratic coming out of a complex pair of roots on the unit circle will be s squared plus 2 into the real part, which is cos 36 degrees, into s squared plus 2 into alpha into s plus 1. alpha square plus beta squared is 1. So, it is s squared plus cos 36 degrees is approximately 0.8. So, 1.6 s plus 1, 36.8 degrees is 0.8. M2 minus N2 you know, so M2 plus N2 will be, this is 72 degrees. So, s squared plus 2 into cosine 72 degrees into s plus 1, straight away images of these will be on this side, alright. So, the real part of this will be 72 degrees, cosine 72 degrees, s squared cosine 72 degrees is approximately 0.3, 18 degrees approximately 0.3. So, 2 into 0.3, so 0.6 s plus 1. So, Zs is, this one will be the numerator, s squared plus 1.6 s plus 1 divided by s squared plus 0.6 s plus 1, approximately this will be the function. Is that okay? So, we have seen how to calculate the function Zs from the phase. Now, from here you can calculate the magnitude. Once you know the actual Zs, you can calculate the magnitude. Sir? Yes, please.
Sir, such type of problems when we encounter in the practical system?
No, in the practical system sometimes we measure only the phase. We are not in a position to estimate, say, the gain. Then what will you do? Okay. Sometimes you try to track both magnitude and phase, all right, and try to find out Zs. It's a cross check. It's a cross check. Suppose the magnitude function is known, we take only the real part or the only the total magnitude with frequency. Then you approximate it by even polynomial ratio of even polynomials, all right, and then only from there you can find out, just previous to this we have found out Zs into Z minus S, is it not? So, factorize it, find out the right half plane roots, left half plane roots, all right, take only the left half plane roots, and that gives you the function Zs. You are tracking only the phase, then from the phase, if you can estimate again phase function in the form of polynomials, then you can estimate Zs. In the laboratory, depending on your facilities available, the accuracy for measurement of phase and magnitude may be different. So, you try to find out Zs, approximate Zs from both sides. Another example, tan theta equal to omega cubed minus 3 omega divided by 1 minus 3 omega squared, all right. So, how much is j tan theta? Whenever the phase function is given in the form of tan theta, we write j tan theta, that will be j omega cubed minus 3 omega j by 1 minus 3 omega square. Make the reverse substitution, s equal to j omega. So, that gives you j omega cubed means minus s cubed minus 3s, okay, divided by 1 minus 1 plus 3 s squared, all right. So, this will give me minus s into s squared plus 3, correct me if I am wrong, 1 plus 3 s squared, all right. So, what is m plus n? What is m plus n? Minus s cubed, just add these two, plus 3 s squared minus 3s plus 1. So, that gives me s minus 1 1 minus s whole cubed. Is that all right? 1 minus s whole cubed. So, where are the roots? All on the right of plane at s equal to 1. So, what will be m1 plus n1 by m2 plus n2? These correspond to m2 plus m2. This does not give any finite roots, that is zeros. So, 1 by 1 plus s whole cubed. Is that all right? So, this is not a driving point impedance, it is an impedance function, it is a transfer impedance function. In case of a transfer impedance function, you may have difference in the degree more than 1, but in case of a driving point impedance or admittance function, we know the difference in the degree should be restricted to 1. Here you can have more than 1. So, this is not a driving point function.
So, why it is so, the difference is 1 and the difference is greater than 1?
Not greater than 1, it may or may not be 1.
For the not having it.
So, transfer function is a ratio between two voltages, say, or voltage and current. So, that transfer function can be anything. It can have only thing, the roots must be in the left up plane, that is poles must be in the left up plane. Okay. So, yes, this is any stable system. Any stable system may have a phase function like this, but this is not a impedance function, a driving point impedance function, not a driving point impedance or admittance function. I will call it emittance function. All right. So, this is basically a transfer impedance. About the properties of transfer impedance we will discuss later on when we go for two-port synthesis. Now, we shall take up one or two more examples. This is all about realization of networks from given parts. Let us take another example, a real part of zj omega, okay, 1 plus omega squared by 1 plus omega squared plus omega to the power 4. What would be Zs? So, yesterday we had handled this kind of problem. So, what will be 1 plus omega squared plus omega to the power 4? Did we discuss about this particular problem yesterday?
Yeah,
1 plus omega squared by, did I take this very example? Then otherwise we will skip to another problem. No, I do not think so. We took up another example. 1 plus omega squared by omega to the power 4. No, no, not this example. Okay. I do not think we did it. Okay, because I have chosen this because we want to see two types of functions given by the same expressions. So, what do you do here? Make a substitution, a squared equal to minus omega squared. So, that will give me 1 minus s squared by 1 minus s squared plus s to the power 4. So, what are the roots of this? S4 minus s squared plus 1 gives me s to the power 4 plus twice s squared plus 1 minus 3s squared. So, it is s squared plus 1 whole square minus root 3s squared. So, the roots corresponding to m2 plus n2, m2 plus n2 will be having the left up plane roots of this. So, s square plus root 3s plus 1, this is the denominator. So, numerator let us assume A0s, A0 plus A1s plus A2s squared divided by s squared plus root 3s plus 1. Okay. So, even part is how much? A0 plus A2s squared into s square plus 1 minus root 3 A1 s square divided by m2 square minus n2 square, which is this. So, if I put s equal to j omega here, I get a real z j omega, okay, and that gives me how much? A0, sorry, A2 omega to the power 4 plus A0 s squared, all right, plus A2 s squared minus root 3 A1. Is that okay? So, A0, so plus root 3 A1 minus A0 minus A2 into omega squared plus A0. This is the numerator. Is that okay? Equate the coefficients. So, A2 omega 4 is absent, so A2 is 0. Next, root 3 A1 minus A0 plus A2, root 3 A1 minus A0 minus A2 is equal to 1, coefficient of omega squared, and A0 is equal to 1. Substitute here, A2 is 0, so root 3 A1 and A0 is 1, minus 1 is 0. So, A1 is 1 by root 3. Therefore, Zs will be A0, that is 1 plus A1s, so 1 by root 3s, A2 is 0, divided by a squared plus root 3s plus 1. So, that gives me s plus root 3 divided by root 3 into s square plus root 3s plus 1. This is Zs. Is it all right? There is an interesting point to be noted in case of synthesis, that if you have a two element synthesis, from the network function you can identify whether it will be a two element synthesis or a three element synthesis. For example, Zs, if you are having functions like s squared plus alpha, s squared plus beta and so on, s squared plus gamma, s squared plus delta, functions of this type, and if the poles and zeros are interlaced, they are coming alternately, then it is an LC function, is it not? LC. You can have Foster 1, Foster 2, Coir 1, Coir 2 realizations, and in those realizations you have minimum number of elements, they are canonic forms. If Zs is having real roots s plus alpha, s plus beta and so on, and if they are interlaced, then they can be either RL or RC depending on whether, for Zs, whether the pole is closest to the origin. The first one starts with a pole or not, then it will be an RC. If the first root is a 0, nearest to the origin is a 0, then it will be an RL function, and we can realize it again by 4 canonic forms. Suppose it is a positive real function, but roots are not alternately coming, then it is neither RL nor RC, it will be an RLC network. This is also what we saw earlier. If it is tested for positive realness, and the conditions are satisfied, then it is realizable. But if the poles and zeros are not interlaced, then it will not be an RL or RC, then it will be RLC. And if it is an RLC network, then we will find now you cannot have necessarily a Foster 1 or Foster 2 realization. You have to go for Bott-Duffin or Bruni synthesis. Well, not that. You cannot factorize it. I will give you an example. You cannot factorize it so easily. Let us see. I will take a simple example. Let me see if I have that. Okay, let us take a function s plus 4 by s plus 1 into s plus 3. Okay. This is a function which we got just some time back. If you remember the first example that I worked out, yes, this is the one, s plus 4 by s plus 3 into s plus 1. Okay. So, how to realize this? It is a positive real function, though poles and zeros are not coming alternately. There are two poles first, then the 0. So, it is neither RL nor RC. So, I thought of trying to realize it. ZS, suppose it is K1 by S plus 1 plus K2 by S plus 3. Obviously, one of them will be negative because poles and zeros are not coming alternately. Let us see. How much is K1? How much is K1? Multiply by S plus 1, put S plus 1 equal to 0. So, this will be 3 by 2. 3 by 2 into S plus 1. So, this will give me an RC combination. Now, here it is K2 S plus 3 is 0. If I put, this will be 1, this will be 3 minus 3, so minus 1/3. So, it will not work. Suppose let us put it as S into this. Then how much is K2? Multiply by S plus 3, divide by S, so it will be S plus 4 by S into S plus 1, and then make S plus 3 equal to 0. So, this will be 3 divided by 1 divided by 3 into 2, minus 2. So, minus 6 plus 6, 1 by 6 into S plus 3 into S. What is this? An RC combination. What is this? An RL combination. So, if someone goes by Foster 1 realization, it is possible for such a simple function, it is possible to get this. Problem comes when you are having quadratics and not so easily factorizable in a factorizable form, then you have to go for Bruni synthesis or Bott-Duffin synthesis. Not necessarily always you will be having that kind of synthesis, even by Bott-Duffin synthesis also you may be landing up in similar functions. All right.
This is not canonic.
Let us see what canonic means. This is Foster 1 synthesis. All right. Means we are putting series elements Z1, Z2, Z3. Let us try YS Foster 2. Then it is S plus 1 into S plus 3 divided by S plus 4, and that is equal to S squared plus 4S plus 3 by S plus 4. Okay. S squared plus 4S by S plus 4 is S into S plus 4, S plus 3 by S plus 4. So, this is a capacitor, and S plus 4 by 3 is the impedance. So, it is 1/3 4 by 3 ohm resistance and 1/3 Henry inductor. This is 1 farad capacitor. Now, you see here you are having 3 elements, here you are having 4 elements. So, ys and zs, you see the difference, alright. If someone goes for coir synthesis, ladder synthesis, let us see what it gives. Zs equal to s plus 4 by s squared plus 4s plus 3, is it not? I can write this as 1 by s square plus 4s plus 3 by s plus 4. So, let us carry out the division, s square plus 4s plus 3 s into s square plus 4s here. So, 3 s plus 4 s by 3 s 4 3 3 by 4 3, okay. So, it starts with 1 by s plus 1 by s by 3 plus 1 by 3 by 4, so 4 by 3. So, what does it give me? Admittance of capacitor, then an impedance of 1/3 Henry and 4 by 3. This is coir 1, okay. Coir 1 synthesis is same as Foster 2, it is the same thing, 1 farad, is it not? It is coming as Foster 2, coir 1 and Foster 2. Coir 2, reverse the order and then see. Zs equal to 4 plus s divided by 3 plus 4s plus s square equal to 1 by 3 plus 4s plus s square divided by 4 plus s. So, let us divide 4 plus s, 3 plus 4s plus s squared. So, this will be 3 by 4, 3 plus 3 by 4 s. So, 13 by 4 s plus s square, 4 plus s, how much is it? 16 by 13, is that all right? That gives me 4, 16 by 13 s in the denominator, all right. So, that gives me 4 plus 16 by 13 s. Now, that gives me minus 3 by 13 s. So, since there is a negative sign, it is not possible to realize by coir 2. Coir 2 does not exist. That means, you cannot have something like resistance and then a capacitance and so on, then an inductance or resistance, it will fail. So, canonic forms of that kind, coir 1, coir 2, Foster 1, Foster 2, all may not be applicable here in 3 element networks. Some of them may succeed, some of them may not. Not obviously, that you have seen just now, I have tried all the 4 methods, and number of elements also differ. In some case we have got 3 elements, in some case we got 4 elements. In Bott-Duffin synthesis we have seen we can avoid the use of that Bruni's transformer with 100% coupling, but number of elements will be more, alright, number of elements will be more. Let us take 1 or 2 examples on ZS with 3 elements, that is Bruni's and Bott-Duffin's synthesis, some of the interesting networks. Okay, sorry, before we go to that, there is another function. Suppose real z j omega equal to 1 plus omega squared by 1 plus omega square plus omega to the power 4. Earlier it was real z was given. Suppose this is magnitude squared. Suppose this is equal to magnitude square, then what will you do? Have you understood? If Zs squared is there, then you make substitution, z minus s will be 1 minus s squared divided by 1 minus s squared plus s to the power 4. Have I done it? Sorry, just now. It was the real part. Yeah. No, I did the other problem. That was the real part. So this will be 1 plus s into 1 minus s. Okay. And how much is this? S squared plus root 3s plus 1 into s square minus root 3s plus 1. Okay. So how much is zs? Choose only the left of plane roots. So s plus 1 by s squared plus root 3s plus 1. Is that all right? Earlier, while computing for when it was given as real z equal to this, we got the same denominator, but the numerator was, if you remember, 1 plus s by root 3, something like that. No, I just,
yes, 1 plus 1 by root 3 s.
1 plus s by root 3, that was the function. So you can see the difference. Yes, 1 plus s by root 3 was there. So that is the only difference in the numerator. Denominator remains same. Okay, now I will take general RLC synthesis by both Bruni's method and Bond-Duffin's method. This is just revising what we have learnt earlier. So realize Zs equal to s squared plus 2s plus 16 divided by s squared plus 2s plus 4. Okay. Let us try by Bruni's synthesis. So what was the starting point? A real z j omega we compute, that is m1 m2 minus n1 n2 by m2 square minus n2 square. So s squared plus 16 even part into s square plus 4 minus 2s into 2s, 4s squared divided by s squared plus 4 whole squared m2 squared minus 4s square n2 square, s equal to j omega. Is that all right? So that gives me s to the power 4 plus 16 plus 4, 20 minus 4, 20, so 16 s squared plus 64 divided by s to the power 4 plus 8s square minus 4s square, 4s squared plus 16. Is that all right? S equal to j omega. So if I put s equal to j omega, omega to the power 4 minus 16 omega squared plus 64 divided by omega to the power 4 minus 4 omega squared plus 16. Now this you can see is omega squared minus 8 whole square. Okay, omega squared minus 8 whole square. So this function becomes 0 at omega square is equal to 8. We have to first of all track that frequency at which the real part vanishes, is it not? So the real part z j omega 1 equal to 0 at omega 1 equal to root 8, that is 2 root 2. Once you have traced that frequency omega 1, calculate z j omega 1, that will be the imaginary part, is it not? That will be the imaginary part. So if I put omega equal to 2 root 2 in this, how much is it? 16 minus s squared is minus omega squared, that is 8, correct me if I am wrong, okay, plus 2 into s, 2 into j into 2 root 2 divided by s squared plus 4. So, minus 8 plus 4 plus 2j 2 root 2. So, that gives me 8 plus 2 to the 4 root 2 j divided by minus 4 plus 4 root 2 j. Is that okay? Now, you can see for yourself, 8 plus 4 root 2, 8 plus 4 root 2 somewhere here, 8 plus 4 root 2, how much is the magnitude? 8 8s are 64 plus 32, 96, square root of 96, okay. Tan inverse 1 by root 2. And this is 4 4s are, you see, somewhere here. 4 4s are 16 plus 32, so root 48 tan inverse root 2. This is tan inverse 1 by root 2, okay, and this is tan inverse, this magnitude is tan inverse root 2, but it is more than 90 degrees. So, how much is this angle? How much is this angle? The difference is 90 degree. It is the denominator angle which is more. So, if this is theta, this is 90 plus theta. Is that all right? Magnitude is root 2 and denominator is having an angle of 90 degree, that means minus 90 in the numerator. So, 90 degree in the numerator. So, minus root 2 j. Is that all right? It is just a simple computation, otherwise also by rationalizing you will get minus root 2 j. I thought it is better to write in the polar form and you can imagine the angles very clearly. Okay. One is alpha, the other one is 1 by alpha, tan inverse alpha and tan inverse 1 by alpha. So, find out the difference in the angle. Is that all right? So, z is known. So, x is minus root 2, I call it x1. So, in Bruni synthesis, if you get a negative reactance to start with, what will that be represented as? L1 is equal to x1 by omega 1, which is root 2 divided by minus root 2 divided by 2 root 2. 2 root 2 is the frequency. Thank you. All right. So, this will be minus half Henry. So, to start with, we will have a minus half Henry inductor. Do not get frightened. In the realization in a transformer, you will find that minus can be accommodated. So, once you have identified this, then you go for the next impedance Z1. What is Z1s? Z1s is Zs minus L1s, which is nothing but, what was Zs? Sorry, s squared plus 2s plus 16 divided by s squared plus 2s plus 4 minus L1s. L1 is minus half. So, minus and minus will make it plus half s. Is that all right? So, add these two, what do you get by adding this? So, s cubed, s square plus 2s plus 4 S square plus 2s plus 16 by S square plus 2s plus 4 plus half s. Is that all right? So, you get 2 into S square plus 2s plus 4, and here it is twice S squared plus 4s plus 32 plus S cubed plus twice S squared plus 4s. Correct me if I am wrong. So, that gives me s to the power 3 plus 4 s square plus 8 s plus 32 divided by 2 into s square plus 2s plus 4. Is that all right? This you can write as s cube plus 8 and s squared plus 8, s square plus 8 into s plus 4, 4 into s square plus 8, s into s square plus 8 divided by 2 into s square plus 2s plus 4. By the way, why did I take s square plus 8 as a factor? If you remember in the network, this function Zs is having a value minus half root 2j at that frequency, all right, and it is also the value of this that we have equated. So, this will be a 0 at that frequency. If you remember, this element Z1s must be 0 at that particular frequency, omega 1. Okay. So, this Z1s at omega 1, that is 2 root 2, that is s square plus omega 1 square will be a factor in the numerator, and omega 1 square is 8. So, s square plus 8 will be a factor, that we know.
So, this is, please explain that part.
Because what we try to ensure is this impedance at that frequency is equal to the reactance at that frequency of this coil. So, what will be the impedance of this? It has to be 0, because this impedance is equal to this impedance. So, this has to be 0. So, Z1s must have a 0 at that frequency. So, s square plus 8 must be having a numerator factor, must be a numerator factor of Zs, this Z1s.
Otherwise, we could have a different factor also in
obviously, we are making it equal to that inductor. Okay, thank you very much. We will stop here for today. We will continue with this in the next class. Good morning, friends. We will continue with the numerical problem that we are discussing in the last class. We took a function Zs equal to s squared plus 2s plus 16 divided by s squared plus 2s plus 4. We started off with this function and we found that at omega 1 is equal to root 8, the real part vanishes, and we also obtained the value of x1 as half s, rather corresponding impedance. This was L1s, all right, and this was minus half s, minus half Henry. This is Z1s, which will be equal to Zs minus L1s, and that gave me L1s is having a negative sign. So, that gave me a plus sign. So, we got s squared plus 8 into s plus 4 divided by 2 into s squared plus 2s plus 4. Okay. To realize a pole, we know we can make partial fractions. So, this 0 is to be converted to a pole. So, we can very easily realize Z1s in terms of admittance function which will be 2 into s squared plus 2s plus 4 divided by s squared plus 8 into s plus 4. We write as k1s by s square plus 8. We know whenever there are roots on the imaginary axis, it will be realized in terms of an LC network, k1s by s square plus 8 plus k2 by s plus 4. This is to be seen later. Let us see what this means. How much is k1? Multiply by s square plus 8, divide by s, make s square plus 8 equal to 0. So, this will give me 2 into 4 minus 8. So, minus 4 plus 2s divided by s into s square plus 8. So, s into s plus 4. So, s square plus 4s, which gives me, this is minus 8 plus 4s divided by minus 8 plus 4s. So, that is equal to 1. There must be some frequency where it is minimum. Omega squared is equal to x squared plus 15x plus 24, x squared plus 17x plus 16. I hope this is all right.
Yeah.
Okay. Then 2x plus 15 into x squared plus 17x plus 16, 2x plus 17 into x squared plus 15x plus 24. So, 2x cubed, 2x cubed, they get cancelled. 2x into, okay, let me rewrite it. Anyway, what I wanted to stress is you will get a real value of x, that is equal to omega square. So, calculate omega and substitute that omega here in the real part. So, that will give you the minimum value, that is when the real part varies like this, it is this minimum value, and after computing that R minimum, subtract it from ZS, whatever is left over you start realizing that ZS, the remainder ZS. There may be a small slip somewhere here, we will discuss it in the next class if time permits, otherwise you work it out yourself, and since there is not much of time. Okay, thank you very much. We will continue with this in the next class.